Your refreshments. So it gives me I'm delighted to welcome our next speaker, David Saunders. David Saunders is the co-chief professor of statistics and actuarial sciences at Waterloo, and is also the director.
I'm going to allow.
Sure. The director of the Center for Financial Industries at the Field Institute. He is the author of numerous articles on risk management, portfolio optimization, and accounting. He's also a co-author with Professor Mary Hardy on the book on quantitative enterprise risk management and funding. So he's going to be speaking to us about statistics for climate policy.
Okay. So oh, it was nice. Sorry, I saw my name there. I thought those were my slides. Yeah, that one. Yeah. Go full screen. Okay, thank you very much for the nice introduction and for the invitation to speak here. And thanks very much to the organizers. I really, having done a number of events at Fields recently, I appreciate how much work goes on in the background for all of the people who are making sure that you can hear me at home and see me properly and all of these things. So I really do appreciate it. I was asked to give a tutorial on statistics for complex climate problems, and a story from pure mathematics came to mind when I was asked to do that. So we have pictures of two famous pure mathematicians here. On the left is, well, your left is Pierre de Fermat, the famous French mathematician, and his famous conjecture at the time, or claimed proof about a Diophantine equation that had no positive integer solutions, which took, he claimed he had a beautiful proof that didn't fit in the margin. 350 years later, mathematicians finally succeeded in proving the result, partially by confirming some conjectures of the other gentleman there, Andre Weil. And I was reminded of this in Weil's obituary, which says that in 1973, an associate professor at Princeton had the temerity to write a biography of Weil's revered Fermat. And the bad luck to draw Weil as a reviewer. Without a doubt, it was the most devastating book review in the history of literature. He begins reminding us that in order to write even a tolerably good book about Fermat, a modicum of abilities is required. Lists them as ordinary accuracy, the ability to express simple ideas in plain English, some knowledge of French, some knowledge of Latin, some historical sense, some familiarity with the work of Fermat's contemporaries and successors, and knowledge and sensitivity to mathematics. And Weil then went to consider each of these requisites one by one and to demonstrate via annotated quotations from the book under review that the author possessed none of them. So I was asked to talk about statistics for complex climate problems. Not a climate scientist. I don't normally describe myself as a statistician, but I will say that I'm a consumer of statistical methods applied to some complex problems, and I'm a collaborator, and I work on some of the theory with statisticians to address those problems. So my role model, or my idol here, is the person with the arrow sign outside the store trying to attract your attention and bring you in. Hopefully, to people who are in science or climate science, say, we have lots of interesting statistical methods that my friends in the department work on and have developed, and to my friends in statistics point out, there's lots of interesting problems here that you might want to address. Okay? And I'll try to do that as we go along, and I'll also highlight, I think, some things that have been, close to my heart and near to some of the work that I've done in the past. Okay? All right, so I'll talk first just very generally about some of the things that we do in finance, climate science, and so on, where we might be wanting to estimate some relationship based on our data, right? So in a very, very general way, we have some explanatory variables, or some X's, the three-factor from a French type model that we saw before was an example of that. And then we have some variable that we're trying to predict. Default of a particular company, precipitation at a particular location, and so on. And then we perform some estimation on that. And we have some errors associated with it. There's some inherent variability maybe in the observations. It's an irreducible error. And then there's some problems with fitting the function, right? And we can fit, depending on the purpose that we're looking at or what we're interested in doing, some very simple models or some really, really complex models, right? And this, of course, involves some choice on our behalf. This is an example taken from an Introduction to Statistical Learning, a very popular book in the field. I apologize, the slides are, it's hard to read, but we have here income predicted as a function of years of education. And the other explanatory variable, I think, is seniority, but I'm not 100% sure. And the simplest model is a linear model. And then we go to a spline, which is a sort of interpolation type model, which balances off the smoothness of the surface with the degree to which I actually fit the data. Right? And we're kind of varying the importance of those two things, right? In the linear model, I do okay. And what I end up with is a model that's maybe easy to interpret and explain, but doesn't do as good a job fitting my data. Okay? Certainly not in the training data set. Okay? And if I crank up the importance of fitting the data well, then I can go through all of my points, but I get something that's very, very complicated and maybe won't do so well when I go to try to predict things out of sample. So depending on the application that I'm interested in, I may choose one or the other or somewhere in between on those very different possible fits. So different Fs may be appropriate depending on what I have in mind. Okay? With more general functional forms, I obtain a better fit, but I maybe get less intuitive understanding of what's going on and possibly problems for out of sample performance. Okay? So as I said at the bottom of the slide there, we have to be careful over fitting. And there's sort of a range that we see as we move from basic linear regression, where I can make inference directly on all of the coefficients and I can understand very well what's going on and write down the function and have a very, very simple relationship. And I may even, and we'll see this a little bit later on in the talk, try to make the relationship even simpler, right? Try to introduce penalties or constraints that reduce the number of non-zero coefficients that appear in my basic explanatory function. So those are the ones that are up here, which have very, very high interpretability, but are not so flexible. And then I can, go to the full scale sort of machine learning methods and very, very flexible models, okay, that live in the bottom right here. Very popular these days. You see them in the media all the time and used in lots of academic papers as well. But then I have a lot of problems with maybe interpretability and trying to explain what my model is actually doing, right? And again, this is a variation of that earlier example we saw. We're working with just simulated data here. What's been done is we took the black curve and added some noise to it. Okay? And again, considered those methods that we saw in the earlier slide, which was to say a pure linear fit, and then allowing a balancing between going directly through the data and having some degree of smoothness in the curve. Okay? And on the left-hand side, we see that sort of trade-off that I mentioned before. If I do a linear fit, I get something that's very easy to understand, describe, explain to the audience, but maybe doesn't do such a good job going through all of my points. And then if I go to the green curve, I'm doing a great job, at least in sample, matching all of my data, but maybe out of sample, I'm not going to do as well. That's the plot on the right-hand side. And also, it's very difficult to explain, okay, exactly what's going on, right? So we saw an example of a linear model in the talk before, where within 30 seconds, we could explain exactly what was going on, right? I have these three factors. I can explain them to you very quickly. and you at least understand what the model is, right? Whatever this green curve is, I'm not likely going to be able to explain it to a general audience in 30 seconds. Okay. Maybe I'll, in the interest of time, go over this slide and move on to those two extremes again, because we're gonna encounter these guys later on again. So I mentioned before, and this is a mathematical technique to try and enforce sort of interpretability, right? So in a lot of fields right now, we're dealing with an explosion of data, right? We have very, very high amounts of data and often very, very high dimensional data, right? So my colleagues in statistics, often they're, you know, maybe they're doing a medical study and they have, you know, information on lots of different measurements of an individual, right? And then they're trying to find, well, among this large biological data set, what are the key explanatory variables that tell me about, you know, a particular ailment, right? So what I want, if I fit, say, my linear regression function or some other function that's supposed to explain the outcomes that I observe, is, you know, a few non-zero, a few important coefficients, right? And the way they can do that, or one strategy to do that, is to minimize here not only the error. So RSS is, I thought I had that equation on the slide. I do. It's the residual sum of squares, right? So that's, you know, I look at all of my errors that I had on my earlier plot and I square them and I sum them up. And this is the usual thing that we do when we're, say, doing a regression model, right? And then we add some sort of penalty there, which is a measurement of the size or the norm of beta, right? My coefficient function. And what they typically choose, the one that I've put here, is to use what we call the L1 norm. So I've drawn here for you different ways of measuring the size of a point or the distance from the origin 0 in our data set. Okay? The light blue curve here with 2, that's the usual way that we measure distance, right? The square root of the sum of the squares of the components, the Euclidean distance from the origin. Okay? And there are various other ones. This red square here just takes the maximum component. Okay? So if I have n explanatory variables, what's the maximum, okay, of the absolute values of the entries in that vector? And the one that's used in this regression model is the purple kind of diamond there, which uses what we call the L1 norm. What I'd really like to use in some sense, if I let this variable that I'm considering p get smaller and smaller, I get down to when p goes to 0, penalizing if you have a non-zero coefficient. Okay? But that's a little bit harder to work with from the point of view of optimization. And this picture here kind of shows you that you can get a lot of mileage just out of using the diamond. Okay? Because if you look at sort of the level sets or the so these ellipses are, you know, curves where this sum of squared errors is the same. Okay? And I want to pull that down while balancing it off against, you know, how big my diamond is or how big my circle is. Okay? What you notice is, you know, my minimizer here kind of usually or often picks off a corner. Okay? And a corner is where a lot of the variables are 0. Okay? So the fact that this diamond is sort of minimally round, so enough that it's easy to work with from a mathematical point of view, but it also enforces that I'm really penalizing the non-zero coefficients. That becomes very useful in these models and lends to, therefore, more, that was dangerous, zeros in the beta, the wire hooked on the keyboard thing, more zeros and therefore a more interpretable model. On the other extreme would be some kind of really complex deep learning algorithm where we pass things through several layers of a neural network and we come out with some prediction at the end. And there are lots of academic papers on this. Again, I've seen this a lot in finance recently, sort of trying to predict, you know, where we're going to predict prices of these things or these several variables, you know, over short time scales and so on and so forth. And of course, here, it's very difficult to explain what's going on, right? Whether it's to, you know, an investor, a regulator, the general public if you're giving a talk. Yeah, I was going to put a particular model here and then I decided against it, right? In finance, one of the acid tests that can be posed to someone who's promoting a model is, would you put your money where your mouth is, right? Would you actually invest based on this thing? And I've yet to see one of these highly complicated things where I would be willing to do that. I'll leave it at that, especially given that I'm being recorded. Okay. So that was a little bit about function estimation and statistical learning and sort of the trade-off between things that we can understand and explain. I should point out maybe one more thing. We've learned a lot, I think, recently about being really careful about statistical models that we don't understand, right? Because any sort of biases or errors or problems with the data that are going in, get translated into the output going out. And because we can't explain the model, we don't know how that's happening. And it can be harder to, at least at first, detect that it's happening, to see it happening in practice. So that's another reason to be concerned or careful, at least, with models of this sort. All right. I want to talk about extremes a little bit, but I want to get there through the sort of standard statistical results that I think hopefully most people have seen, at least explained in general terms, if not in statistical courses, right? So a lot of the basic statistics that we learn as undergraduates is based on averages. Okay? So, I flip a coin and I count up how many times I get heads out of, say, 1,000 coin flips, right? Or 10,000 coin flips or whatever, right? And we expect that that frequency should come pretty close to 1/2, right? And the more times I flip the coin, I should expect the frequency to be closer to 1/2, right? And and in fact, if I see that that frequency is very far from 1/2, okay, then I think that maybe something is up, right? Something's wrong. I was preparing these slides on Saturday, and I was very concerned that I was going to have to use the example of a hockey team that lost 13 consecutive games when they had the chance to clinch a playoff series. But instead, I found the other example when I was trying to plug in the USB stick to load my talk, right? Which is, for some reason, every time the wrong way. Okay? All right. And there's math on this, right? And we know that we expect some sort of convergence as the number of coin flips goes to infinity and for very, very general sorts of random variables, right? But my friends and colleagues in the statistics department know a lot more than that, right? So they also know about, okay, I repeat this experiment, I flip the coin 1,000 times, and I look at my frequency and I compare it to 1/2, right? And it's probably not going to be exactly 500, right? Sometimes it's going to be a little bit more, sometimes it's going to be a little bit less, right? And I can repeat that 1,000 times experiment thousands and thousands of times. I have nothing better to do with my life. Okay? And we know what that distribution of fluctuations tends to when we're looking at averages, right? Typically, under reasonably general assumptions, it converges to a bell curve. Right? And you can see that I gave on the slide there a physical manifestation of that, the Galton board or Plinko, if you're familiar with the Price of Right, where Price is Right, where you get the binomial distribution as it goes one side or the other, right? All right, and they know more than that. They know about this at the level of processes. So if I observe lots of random variables together across space or across time or several different levels of a given random variable, this is for just a uniform 0-1 random variable, right? So what your computer is supposed to be giving you when you use rand in Excel or something like that. We know that's a deterministic function, but the same idea, a random number between 0 and 1. Okay? And I look at, well, okay, I do that 1,000 times. How many are below 0.4? It's supposed to be 400. How many are below 0.5? It's supposed to be 500 and so on, right? And they know all about the variations of those and how they vary together, right? And the law for the fluctuations of that. Okay, and all of that, as I said before, is about averages. Okay? But in a lot of applications, we're not interested in averages. And you can insert your own joke here about your head being in the oven and your feet being in the freezer and you're fine on average, or you drown walking across the lake that's 3 feet deep on average, and then so on, right? We're often interested in finance. We looked at market crashes, 2008, 1987, and so on. Okay, in climate, often extreme weather events. We're interested in extremes. All right. Now, the good news is that my friends in the statistics department have also spent a lot of time studying distributions of extremes. And there are various approaches to this, and I gave you the pictures that correspond to each of those. So one approach is to look at what they call block maxima. Okay, so maybe I look at my block size is 1 year. Okay? What was the maximum return that a stock had in any given day over a year? Okay? And then I look at that over several years, and each of those years is a block. Okay? And there's a limit theorem if I look at here. So this would be the maximum of my daily returns, right? Or maybe it's temperature observed in a given month. Okay? And I look at the maximum temperature over several observations. Okay? And we get a limiting distribution here. It's a little bit more complicated than what we show in the undergraduate courses about the normal distribution. Okay? In particular, my normalizing sequences, I can't give them to you explicitly for all conceivable random variables, but it's very well understood by the statisticians and the sort of limiting distribution that you can expect to see here. Okay? Comes in a few types, although you can pile them all into one sort of generalized family as well. Okay? That's one approach. Another approach is to look at all observations that go above some threshold. Okay? So I'm going to look at all the days that we lost more than 5% or something like that. Okay? And then I push that threshold bigger and bigger, and there's a limiting result. All of these are asymptotic results, although much like with the central limit theorem and so on, they know things about the speed of convergence in some cases and so on. Okay? So this peaks over threshold. Rather than looking at the maximum each year, I look at all of the observations that lie above some threshold. Okay? In both of these cases, when you try to apply these results in practice, there's a trade-off. Okay? This is a limiting distribution for the maximum of observations as the size of the block. Okay? So the size, the number of days that I'm looking at tends to infinity. Okay? It has to be big. So if I have a fixed data set, in order to apply this, I want lots of blocks. Okay? That's part of the problem, and we'll get to that. There is some work. I'm presenting kind of the most basic results here because I have an hour and I can't do all of statistics. But good point. But the point I was trying to make was even a lot simpler than that, which is not only do you need to assume independence for this particular theorem, but if I want lots of blocks, I have to make my blocks smaller, right? Unless I can go get more data, right? But smaller blocks mean I'm dealing with a less extreme distribution. It's the same thing with the other one here. This is a limit as my threshold goes to infinity. As my threshold goes to infinity, I throw out all my data. Okay? And I have nothing left in both cases. When I want more blocks here, that means I end up with less data to estimate these curves. And when I increase my threshold here to get closer to the theoretical result, I'm throwing out more and more of my data set. Okay? So this is a sort of trade-off that one is plagued with when we look at the theory of extremes. Okay? I'll give you one simple example, which my co-author created for our book, available from fine booksellers everywhere, which is with hurricane loss data in the United States. So you can see definitely some extremes there. You can see Andrew, you can see the Katrina and Rita, and so on. This is all adjusted for inflation to 2017 values, which is when she did that. It shows how bad I was as the bottleneck because it took 5 more years for the data to come out, or the book to come out. Yeah,
Sorry, truncated data, because it's only a storm defined as a hurricane.
yeah,
right?
that's right. Hurricanes and tropical storms, but
Hurricanes,
yes,
storms,
yes.
that's gonna mean a lot. Like, but aren't these data power law distributed?
Yes. Yeah.
Okay.
And
How does that?
we'll get to the importance of tails. So that governs the tail parameter. So actually here is exactly an estimation of the of that tail parameter, which governs how you see decay.
For sure, but then also if we're assuming, making assumptions about normally distributed data for different properties or estimator, I might have to this question 10 years ago already, but so what do we do? When we don't have power like we get with data? I hope you have the answer.
I have points for the answer. I mean, we can work with power laws. There's a large literature on working with power laws. What we can't do is use Gaussians when the data is powerful. And that has been, or should have been, certainly drummed into people who worked in finance a long time ago, because financial data, returns data, also share that property. If you think about, for example, the crash in 1987, and you fit a Gaussian distribution to market returns before that, a daily move of that size should have happened once every several ages of the universe, kind of thing, right? So, and there's an example later on as well. One of the messages, I guess, that I'd like to convey is that understanding the tails and working with the correct distribution for the tails is extremely important. Okay? This example, I mean, I'm not able to move anymore, so that's interesting. Let's see. No, maybe I'll click somewhere and see what happens. There we go. Yeah, so I mean, I'm not concerned so much about this particular method. It was, a very, very elementary example. We do find a thick tail with this data, not surprisingly, and are able to perform at least some estimation here more as an illustrative exercise. I will point out what's reported here as a percentile, and this is something in particular that will vary significantly, whether you're assuming a Gaussian tail or a power law tail. It's okay. One of the challenges, not a major challenge, but when you speak to a multidisciplinary audience, is terminology, right? So later on, I'm going to talk about Gaussian process regression, which you might call Kriging or by some other name. And I'm going to talk about principal components, if I have time, which you might call empirical orthogonal functions or something else. This risk measure, which is the expectation of losses given that losses exceed a given percentile, we've got 5 names for it just in finance. Okay? You probably have something else in another field as well. Okay? But that's what it is. So this is the expectation of the loss given that the loss exceeds a percentile. We used expected shortfall in this particular case, but you might know it by something else. It's anyway. All right, so some challenges that arise in this, particularly when we're maybe thinking about applying this as well to, well, both to financial models and to climate models, is the challenge of non-stationarity, right? We talked before about how well does the data from the past actually serve as a guide to the future, whether it's because there's sort of a recognizable change in coming from climate change, or it changes in the economy. It's the structure of the economy being affected by climate change, being affected by social change, and so on, right? I mean, if I can't go back 100 years if I want to study, or even the length of the time series that we have here, if I want to study exchange rates, right? Because then all of a sudden I get into a system of fixed exchange rates, right? And the data just doesn't make sense to apply to what we're using today. Okay? So again, I want you to think of me as the guy with the arrow, okay? Not giving sort of a complete talk about everything that we do at the moment. So there is work on, the timing and clustering of extremes, on generalizing some of those really basic, first results that I showed you on the earlier slides to non-stationary data, to data that have the spatial extent as well as just a time series. Right? And again, I'm happy to point people to references, or even better, introduce people to colleagues who are far more knowledgeable about a lot of those things than I am. Okay? I found one paper where sort of extreme value theory and this difference in the tail of the distribution was studied in the context of climate risk, which was in trying to look at basically, they say, well, this hurricane that occurred recently, how much more likely is it because of climate risk, right? So what is the effect of extreme climate events, and how have they been affected by anthropogenic forces? Terminology that I'm learning as I read this literature. Okay, so basically what they did in general is you may look at a bunch of climate models and remove the assumptions of increased carbon output because of human factors, and then compare to the factual model. So the counterfactual model here is people haven't been spewing carbon into the atmosphere for as long as they have, and then we compare its output, simulated output, to the factual model, which is calibrated to the actual conditions, and you look at the comparison between the two. This is from that same paper, a very basic stylized example where we look at, so again, factual world that's, in the presence of global warming or anthropogenic climate change. Counterfactual is with that removed. And we're looking at the probability of a particular variable exceeding some threshold. And this, again, is actually a Gaussian and Pareto comparison once again. On the left-hand side, we have Gaussian distributions. I'm told, and I have no personal experience working with this data, but this is a better representation of some temperature data that you see, and this is closer to what you see for some precipitation data. But I'm very happy to be corrected by people who know a lot more about climate science in even a more brutal way than Weil did to the biographer of Fermat. Okay. What we see here is that because of the thick tail of the Pareto distribution, so both times, as we go further and further into the tail, it's more and more likely we see extreme events. They're driven by that anthropogenic climate change. But we're more confident saying that in the case of Gaussian distributions. Because if you see a tail event for the Gaussian, you must have shifted the distribution. Right? The counterfactual distribution, the tail is just so thin that you can't get out to what you're seeing. Whereas with a Pareto, even in the counterfactual world, the tail is very thick, right? So that's just the message from that. And the general message from that set of slides is we need to pay a lot of attention to tails and to extremes, and statisticians have a lot of tools to help us do that. I'll skip this slide.
Okay, on that slide.
Yeah, this one?
Not this one, but the next slide.
Oh, then I skipped this. This is a Gaussian threshold model.
Okay, what distribution is this plotting?
Okay. No, it's okay. I want to make sure that I get through it. This comes from the model that underlies the credit risk. So this is one that I want to kind of slam, and I'm okay, I think, criticizing it because it's public and very popular and so on. It's the basis for the credit risk regulations in the Basel Accord, which is the Basel Accord is the sort of international agreement on how they're going to regulate banks. Okay. And I've talked a little bit about sort of non-Gaussian distributions and how I think they're important. Because of their convenience, we will torture multivariate Gaussian distributions in so many ways to use them in order to be able to generate output. I've been learning as I read preparing for this talk that this is done in some climate models as well. We have threshold models, and you take a multivariate Gaussian, and then if it exceeds some or if a particular component exceeds some threshold, then something happens, right? And that allows us to transform it into something that might look like this, where the green curve, for example, is very skewed. Okay, what this is we have a bunch of loans. Let's say we got 1,000 loans, and to each loan we assign a component of a multivariate normal random variable. Okay, and they default if so. the institution will have some internally estimated default probability for the firm, coming from the sort of model that was described before the break. Okay? And then you say, okay, that's the threshold for that component of the Gaussian distribution, right? So if that Gaussian random variable, that component falls below that threshold, that firm defaults in your model. Okay? And then we add that up over all the components of our multidimensional Gaussian, and rho is I've assumed that all the firms have the same correlation with each other. Which is a bad assumption, but that's what's done in very, very simplistic credit models. Okay? And so if rho is close to 0, then everybody's defaulting close to independently, and curve, because it's very close to the central limit theorem that I showed you before. Okay? And if rho is very high, I mean, if everybody was perfectly correlated, then you get a 2-point distribution. Basically, everybody defaults at the same time, or everybody doesn't default, right? Okay? So you get something more like the distribution there. Okay? But what I wanted to emphasize is that correlation, okay, we all hear correlation doesn't imply causality, but it also doesn't really do a good job of describing dependence. Okay? And that's sort of what I wanted to talk about in the next few slides, is the tools that my colleagues have for modeling, estimating, and calculating bounds based on dependence. I think this is important both within discipline models. So it's certainly important in finance, and I'll talk about that in a second. I think it's probably important in climate modeling as well. And it's really important, I think, when we're trying to draw models from different disciplines, right? Where it's maybe very difficult to estimate a fully calibrated joint model of all of those factors at the same time. Okay? So understanding how we could model the dependency between those factors, okay, and the range of results that we could get depending on how we choose to model the dependency, I think becomes very important. Okay? So that's why I like this slide here, or one of the reasons why I like this. This is what I did was I simulated a bunch of points according to different dependent structures. But the data here follows a pattern. So in each of these pictures, the marginal distribution for X and the marginal distribution for Y is the same. It's Gaussian. Okay? And for each of these pictures, the linear correlation coefficient, so what I get if I ran a simple linear regression, is the same. Okay? All right. But you see that the cloud of points that I get from the distribution is actually very different, right? So one of the issues with the regression models that was talked about before the break, and something that we commonly see in finance, is that people say, like, in a crisis, all correlations go to 1, right? Everything goes to hell at the same time in 2008, right? And in 1987, you have a market crash. So it might look something like this, right? And you can get into a lot of trouble if your risk model assumes something like this, when the real dependence model or structure is something like this, right? And there's good evidence that that was a contributing factor, although there were several, to what happened in 2008. So I have, I went too far. So what I wanted to say here, I wanted to give one example of a financial institution that failed in 2008. This is AIG, an insurance company, but it didn't get into trouble because of its insurance business or its classical insurance business. It got into trouble because of its trading in the credit markets. And its partners got into trouble, its trading partners, and were bailed out to the tune of tens of billions of dollars by governments, mainly the US government, because they had misestimated sort of the joint probability, the dependence that AIG would get in trouble. They probably misestimated that probability, but also that AIG would get into trouble when they owed them a lot of money. Finance, they sometimes refer to that as wrong way risk, right? It affected the, although they really should have known better, the subprime lenders as well earlier in the events that led up to the crisis. What do I mean by that? Lots of people defaulted on their houses, and they did it when the amount that the bank would recover, right, through foreclosure was very low, right? So those two variables, the probability of default occurring and the loss conditional on the default occurring, were not independent, even though lots of models treat them as independent. Right? And something similar happened here with AIG. Right? So again, I on the earlier slide there, I threw out that word copula. That's a tool that allows us to combine marginal models or marginal distributions into a joint distribution. And if you saw on the slide with the clouds of points, I had the names of various copulas there, right? And you can see that they have very different dependence structures. The Gaussian copula, this one here, which comes from the multivariate normal distribution, which went into building up that loss model that I showed you earlier and is the Basel foundation for the regulation of credit risk for banks and so on, right? You see that as we go out into the tail, things look independent. Okay? Extreme losses for X and extreme losses to Y, aren't that correlated. Compared to say, this is a model for correlations go to 1 in a crisis, right? Everything goes to hell at the same time. Okay? And a T distribution has a little bit of that dependence as well, and so on, right? Okay. So copulas provide us with a flexible tool to model dependence, also to, again, consider different dependent structures and look at the sorts of output that we would see if we had different types of dependence between our individual models or individual variables. And my colleagues in statistics have developed a lot of tools to be able to estimate these, to be able to. So one problem is that, and I'm not going to go into the details of this, but copulas are really easy to work with in 2 dimensions. Okay? And then when you get to high dimensions, there aren't so many families that work very easily. I'll give you a simple example. Perfect dependence, right? So I can ask you all, and don't actually do this, to stand up or to sit down at the same time, right? And I can say, please make sure you're all standing or sitting at the same time. Okay? But I can't ask, you sit whenever she's standing and stand whenever she's sitting. That's okay. There's 2 of you, that works. Okay? But once I get to the next row and say, okay, now I want Malika to stand when either of them is sitting, right? It breaks down, right? Because people are trying to stand and sit. So that counter monotonicity works only in 2 dimensions. And then now I don't have a copula anymore. Okay. So there's a lot of work that my statistical colleagues have put into taking bivariate copulas and combining them with various graphical representations of dependence in order to build multi-dimensional, dependence structure. And these are all examples of what are called Vine copulas that I've drawn on here. I have 24 slides left, so I'm not going to have time to go into details about that. Okay. Another thing that statisticians and mathematicians are really good at is coming up with bounds. Okay. He's not here, but the famous mathematician G.H. Hardy attributes a quote to another famous mathematician, Harold Bohr, the brother of the famous physicist, saying that analysts spend half their time in the library just looking for inequalities that they're not able to prove themselves. Okay? What we have here is Monge on this side and Kantorovich on the other side. And what Monge was interested in is I have a distribution of mass over here, and I want to move it to a distribution of mass over here, and I want to do it in a way that minimizes cost. Kantorovich was interested in economics as well, and he came up with sort of a relaxed version of this. Monge said you have to take all the mass from this point and move it to some point over there. Okay? So he wanted a mapping, which I've denoted by T there. Okay? Kantorovich just said, okay, I've got a distribution for X, I've got a distribution for Y, find me a joint distribution for X, Y that minimizes some cost function. I have no markers, C of X, Y. Okay? So that's a bound on an output from a multivariate model, given that I know the marginal distributions. Okay? And that's a relatively nice optimization problem. It's linear. Okay? And we can do lots of easy computations based on it. And there's a huge mathematical theory sort of backing up and understanding those models. Okay? So I think that that can also be used in a lot of places. I have a model for, let me take my example from before, loss given default, and I have a model for probability of default. So now I have two marginals whose distributions I know, but maybe it's very hard to estimate the joint distribution. Or maybe I have a climate model and an economic model of some sort, and I want to combine them. But I don't have a good way of estimating the joint dependence structure. I can at least find out, what is the maximum cost? What is the minimum cost associated with that? And there's been a lot, as I said, this is a very, very active area of mathematics and statistics right now. So for example, they know, well, if you don't have the exact distribution, but you have some approximate distribution or some simulated distribution, how close is the problem on the left here to the problem, the true problem that I'm interested in solving, the problem on the right? And both Monge and Kantorovich were interested in minimizing cost or some expectation, right? So E of C of X, Y. But there's also work where, rather than expectation, we can look at some measure of risk associated with that and still be able to treat that problem mathematically and come up with the same sorts of estimates. And you can add in partial information. So maybe I don't know exactly the joint distribution, but I know it lies within some class of distributions, or I have some idea, maybe I know the linear correlation between X and Y, like I had on my earlier slide. But there's still a whole huge range of joint distributions that work with that linear correlation. One thing I want to say, and I apologize if this is going to be a bit of a non sequitur because I only thought of it now. But the crisis and the credit risk talk reminded me of it. I'm a little bit wary. So there's talk about considering climate scenarios by financial institutions and so on. Personally, I'm a little bit wary of them doing that if it's not backed up with some real regulatory force. So there was a discussion also about how Canada sort of weathered the crisis better than a lot of other countries. And yes, maybe oil and gas contributed to that, but I think a lot of it was also that we had stronger regulations of financial institutions, particularly than what they had in the United States. They did have scenarios. It's well known that their scenarios were not extreme enough, but I'm being recorded. I have a friend who worked at let's call it a financial institution in the United States that no longer exists. And he told me, every week I put on the chief risk officer's desk a report that said, if the property market in the United States, southern United States tanks, we will cease to exist, right? Like we will be in huge trouble. And they did nothing. Okay? So I am concerned that there needs to be, regulatory action and regulatory force behind it. Also, it was talked earlier, and okay, this is climate data, so I can get to this. The role of model averaging in a lot of the climate simulations and so on, right? Because that individual models can produce very different results. So can financial models. Okay, and there are studies done where regulators give different institutions the same portfolio and the same scenarios and say, use your own models and tell us what happens to the portfolio under this scenario, and they get vastly different results. Okay? And financial models don't like financial institutions don't like disclosing the models that they use because they're also really good at screwing each other, right? And if I know the model you're using, I can, take advantage of that in some way. Yeah, I could go on for a while on that, but anyway, this is the use of that same optimal transport problem, except now to define statistical distances, excuse me. So this is chlorophyll data comparing results from satellite observations against a particular model, the Darwin model, it says here. Please don't ask me to explain what that is. I'll be worse than the biographer of Fermat. But what you can see is sort of patterns in the difference. So what we have here is each pair of points is either output from the model or observation of the satellite, and it's through time. So you can see some seasonality in the data. If you had really, really great eyes, you can see zeros along the diagonal because the difference between the two statistical, these are mass distributions across a region of the ocean. Okay, and it's of course it's zero when you look at the exact same time in the exact same area under the exact same observation set. Okay? So this compares and it illustrates a couple of things. It shows very clearly, for example, the seasonality in the data being less pronounced than in that particular model. We also, I think, see that here. No, sorry, this is a comparison of. So again, we're using the statistical distances. This is a comparison between the statistical distance and the point-by-point distance. In other words, if I just added up essentially what I called the Euclidean distance before, all of the observations at each individual point, squared them and took the square root, right? Compared to what's the minimum cost that would take me to move the one distribution into the other. And you can see that I get significantly high. They got significantly different results. So that's another way in which these tools for bounding outcomes and bounding functionals of joint distributions, okay, based on partial information on marginals, I think can be very useful. Okay, and certainly there's a huge literature and a lot of activity on those measures of statistical distance now. Okay. All right, I'm a little short on time. I want to talk a little bit about dimension reduction as another tool for hopefully assisting with interpretability. Okay. So it's a way in which we can identify sort of key sources of variability and improve the interpretability of the data. I gave a picture of a more sophisticated dimension reduction technique and a neural network here called an autoencoder, where I put in data and I use that data as the output as well. And I try to have a smaller number of hidden layers here, or smaller number of hidden neurons, right? So then basically the coefficients for these inner neurons give me the reduced dimension of the data. Right? So rather than expressing it, say, as n coordinates, okay, I give, if I have, say, 3 inner neurons here, just those 3 numbers. Right? It's a nonlinear and more opaque, admittedly, dimension reduction algorithm compared to, say, principal component analysis. Right? So this is a very traditional form of dimension reduction. It works with the measure of dependence that I just spent a lot of time sort of criticizing, which is linear correlations and covariances. So there are some potential issues there. But it looks at sort of transforming the data or the coordinate system really in a linear way, so that the first coefficient it represents a linear combination that maximizes the variance, the variability of the data among all linear combinations, and so on. Second is the direction that is uncorrelated with the first that maximizes the remaining variability in the data. Okay, I'll show you another financial example. I think I have a climate example as well. So there was an interesting discussion going on here during the break about sort of attempts to mathematize, that's a word, economics, right? And try to the physics envy of a lot of economists. So we really don't have laws in finance or economics in the same way that one would in a physical theory. But we do have some, I'll call them stylized facts, observations. One was alluded to earlier this morning in the relationship between risk and return, right? So generally speaking, if you want to expect a higher return, you're probably taking on more risk, right? This is why, high yield bonds pay a higher interest rate. The slang term for them is junk bonds, right? Because the underlying borrower is maybe not as creditworthy. Right? What I have here is another sort of stylized fact. Okay? This is principal component analysis for changes in the interest rate curve. So we talked about the time value of money earlier in the discussion of net present value. Right? And in reality, there's not just a single interest rate. If you want to borrow for 1 year, it's different than if you want to borrow for 5 years, and if you want to borrow for 10 years, and so on. All of these are different interest rates. And we, plot that interest rate as a function of the period, the maturity of the loan. And we call that the interest rate curve, or the term structure of interest rates. And it changes through time. And that's what I've plotted here for the UK government. And so we can look at changes in that interest rate curve, or certain points on the interest rate curve. Let's say I take annual maturities going out to 30 years. So I have a 30-dimensional observation, and I may look at, relative changes in those 30 points. That's a 30-dimensional random variable. It's not so nice to work with. Let me skip this slide. When we apply principal components, what we almost always see is the following. And this is why I call this a stylized fact. The first principal component, the direction of main variation, is parallel shifts. All the rates go up or all the rates go down. And usually, and you can see this repeated for different markets over different time periods and so on, that explains somewhere around 85 to 90% of the variation. A really big percentage. The next principal component is a change in the slope. So short rates go down, long rates go up, something like that. And the third principal component is some sort of bowing. So the short end of the curve and the long end of the curve are both going up, and the middle is going down a bit. And again, we see that. So, really we can represent a lot of these moves of the interest rate curve from, really those 3 dimensions of random variation rather than 30. Now, here's the reason why I showed this financial example, because I wanted to warn you about something in models. So a lot of times, traders and other, we talked about relative performance before, but traders may be compensated based on, the return they generate and the risk they take, right? So I'll make it very simplistic. Imagine that they're compensated. So they get a base salary and then they get a bonus. And the bonus is a function of return divided by risk. So if you generated a lot of return, and we measured your risk as very small, then you get a really big bonus. And if not, we fire you and you go down the street and get a job at our competitor. All right. Bow and tie. Imagine that you were an options trader, and imagine that you were ethically challenged. You might say, I repeat myself. What would you do if you knew that I was measuring risk according to this model? So I only was looking at the first 3 principal components. Take a super risky position that depends on the 4th one. I'm not looking at that in my model. Super risky means high expected return. That's a big numerator. I'm measuring very low risk in the denominator. So in any time where you're using a statistical model like this, and you're throwing out dimensions or you're throwing out information, you've got to be really careful that that information isn't critically important for the application. This is not, by the way, an entirely made up example. There are portfolios that you can find that have been constructed to depend on things that wouldn't be picked up by a risk model like this. And again, my colleagues in statistics have a lot of experience and information understanding that and looking at the responsiveness of the key output variables to this and making sure that your dimension reduction is suitable to what you're interested in measuring, not just in a naive look at the variability of the data. This is a climate. I need my notes for this one. This is ocean. This is water. This is pressure at sea level. Sorry, data in the northern hemisphere. I think it's supposed to be above 20 degrees. And these are the first 2 principal components of a time series of measurements of that. And they explain so far less of the variability than the interest rate curve, but you see a lot of patterns that emerge. Somebody help me out here. Arctic oscillation. is evident in the first principal component. Okay? And I forget the name for what's going on in the second one. I'm sorry. And it becomes clearer when you combine principal components with what I showed you earlier with the diamond. Right, so there are more sophisticated methods of dimension reduction and so on, where here the North Atlantic oscillation becomes much clearer. And especially here, this is the parameter which governs the strength of the penalty that wants to push you into that smaller diamond that I showed you in the earlier slides. Okay? Again, my colleagues in statistics have done a lot of work on generalizations of the basic correlation or covariance-based principal component analysis or empirical orthogonal functions that you saw on those slides. Okay? And so I'm very happy to provide references or even better introductions to people who know far more about this than me. I think I'm out of time. I wanted to say a little bit about data. This is something that I'd love to sell to my statistical colleagues. I looked just last night because it was getting much more entertaining than the hockey game. At this recent paper looking at the Argo array of temperature and salinity in the ocean and interpolation methods. So statistical interpolation methods. I think climate data and oceanic data in particular, but a lot of the other climate data looks really, really interesting for studying with statistical interpolation methods. So things like, again, I would call it Gaussian process regression, but the person next door might call it Kriging, or there are these other names as well, currently. Especially in this data set, because there's lots of, I have to skip over this, but lots of interesting properties that make it challenging, right? So statisticians recently have spent a lot of time improving covariance estimates. Okay? 1,000 years ago when I was a graduate student, JP Morgan used to put out a covariance matrix of risk factors in finance. We grabbed it, we looked at it, we found that you could produce linear combinations of the variables that had negative variance according to their covariance matrix. Okay? Statisticians have done a lot. It is a high dimensional problem. So, but they've done a lot to improve estimation of covariance functions. In the examples that I've seen, they only interpolated one variable, the temperature, not the salinity as well. From physics, we get real qualitative constraints about how these variables should change together. You know, we're looking at pressure at different depths and so on. And I've seen a lot of work on sort of shape preserving interpolation in other areas of interpolation, but not so much in statistical interpolation. So again, now I'm talking to my colleagues in the stats department. I think there's a lot of cool problems here, and sort of these are floats that are doing this measurement, and so they move, and how they move is not entirely uncorrelated with, you know, the data that you're trying to interpolate. So there's lots of really cool problems here. So any statisticians who are still here, I'd love to talk to you about that. I think that's probably a good place for me to stop. I'm happy to talk to people. If you want to buttonhole me, I'll be, when I'm not recorded, more brutal in my assessments of some of the financial models. But I'm happy to answer any questions. But I also don't want to keep you from lunch. I made that promise, and we're pretty much right on time. So thanks very much. Yeah. And I'll make the slides available so you can, you know, look at all those references. This one? Yeah, this is just general lessons. I think there's a lot of opportunity for collaboration and cooperation and so on. And there's a lot of stuff that I didn't talk about because I didn't have all that much time.
So if anyone have any questions, we'll have a couple of minutes for questions before we go to lunch.
I have a question about the slide number 25.
Wow, okay.
You numbered them.
Well, LaTeX numbered them. Yeah, this, okay.
Yeah, so I'm wondering about low is trying to the graph is the gain on is different. Why is it like that?
Okay, so the question here is as how the distribution varies as rho changes, right?
Yes. So all of the rows and the similar behavior, like the Gaussian distribution or something like that.
So when you have, so what I'm doing here again, I took a multivariate Gauss, 1,000 dimension. Okay. And I have you default if you fall, your component, the Gaussian distribution falls below some threshold. Okay. Rho is your covariance matrix is like ones on the diagonals and rows everywhere else. Okay. All right. And then the loss, you just add that up over all 1,000 loans. Okay. So simple. Okay. So if the loans are uncorrelated, if rho is close to 0, I'm adding up a bunch of basically independent things. So I should expect something like a normal distribution, and that's what I get with the red curve. Okay. As rho increases, I guess, again, if rho was 1, okay, then either everybody would be defaulting or everybody would not be defaulting. So I'd have a probability mass here at 0 and a probability mass here of going completely bankrupt. Okay. So as I increase rho, we move from that one extreme, close to a Gaussian, to the other. Okay. So you're going to get more skewed and you're going to get a heavier tail. Still not as heavy as it should be when you use this as an approximation of, like a Clayton type of dependence that I showed you on an earlier slide. Okay? But that's what's going on here. I'm changing that correlation parameter in that matrix within that Gaussian threshold model. Does that answer the question?
Yes. Thank you very much.
Yeah. I'm going to move away from the stunningly bright light. Sorry, go ahead.
Are all is the intensity of the relationship to play a role in the market or we are care about
So it would depend to some extent on what you were trying to do. In this case, I intentionally constructed these so that they would have the same linear correlation, right? So the point was to show that if you only looked at linear correlation, you're missing a lot about the potential dependence structure and the potential variations in the dependence that you can see. There's a lot of flexibility, especially when you can piece together different copulas for different components. There's also a lot of comonotonicity in a lot of applications. I mean, in finance, for example, and so on. But there's a lot of flexibility that's available. By the way, my colleagues in the Department of Statistics very recently published a paper in the Journal of Data Science using this for climate data in Canada. This doesn't bind copulas. Yeah, go ahead.
So if you go back to the other slide you had on the different bullets.
This one?
Yeah, so food for thought. The one bottom right is much closer to stock prices. In terms of all going down at the same time is highly correlated, but all going up is not highly correlated. And in hydrology, it's the opposite. The one on the bottom left is how you would see it, because when storms come, they all come and then highly correlated in the high flows, but lowly correlated in the low flows. But interesting thing would be to find the joint distribution, because in many cases, one after the other and so on, at least if you're an insurance company, for example.
Yeah.
I don't know if anyone has done that.
Yeah. So bivariate is tricking you a bit though, right? I mean, you can, yeah, you can, yeah. So I mean, the point is that you can have copulas certainly give you this flexibility to have dependence in one tail, but not in the other, right? The T copula gives you dependence in both tails, for example, right? The Gaussian gives you dependence in neither.
And with my copula, you have 2 choices too. Like depending on how.
There are, but there's a lot of work on estimating them, and so again, I'll refer you to my colleagues who know much more about that area than I do.
Okay, we have no more questions. Thank you very much. We have a small gift card.
Am I supposed to be smiling? Someone bring a picture or no? Oh, take the money and run. I like this. Oh, we are taking it. Oh, okay. All right. Thanks very much.